wideband technologies, and NXP is investing a lot on this new technology. Today we have 3 experts from NXP. Mr. Vijay Chachra, not visible on the screen, but yes, he is our key leader in enabling UWB technologies on different NXP SoCs. He is having 21 plus of industry experience, mainly driving SoC validation activities in NXP. The second one is Srivasta. He is having 18 plus years of experience in the area of embedded system design and software development. His expertise nowadays relates to the system architecture, and he is having 2 patents in his name and 12 plus patents in the pursue state right now, mainly in the UWB. So we have a great, knowledgeable guy here who can share insight on how UWB is going to change our life in near future. Then we have a special guest, not guest, I can say, our expert from NXP Austria, Mr. Pablo. Welcome to this platform, Pablo. This is a platform where most of the students community is our attendee here, and they are going to be benefited with NXP new technologies introductions, and we can suggest them how they can shape their careers on future technologies. And NXP is ready to support from all aspects to support them, the students, researchers, professors, lab, the guys who are managing the lab and all. So Pablo is the key, you can say expert in the UWB domain in NXP. He is from Spain, but now, part of NXP Austria. He did his PhD in ultra wideband technology, which is, you can say that value add on UWB. So without, investing much time on the introduction part, I am handing over to Vijay, who is going to brief us about what is UWB and how NXP is basically, developing and driving different embedded systems, different types of segments, which includes automotive, home automations, and other emerging areas in the wearable segment. So over to you, Vijay. Vijay, please unmute yourself.
Yes. Hello.
Great.
Good evening, everyone. And thanks for joining. I think as Manish said, we are putting the ground together with 2 of our experts. I just support these activities from the validation side, but I would call Srivatsa and Pablo as a real experts, as a domain experts on these particular topics, right? And the way we want to take forward this is introduce you to the sessions where you have a view of what the UWB technology is. But before that, we will start with something which is very fundamental in nature. And what do you call as fundamental in nature? Let me just share my screen for a minute so that you get a view of what's going on here. Yeah. Let me know when you guys can see it. Right. So overall, when we talk about any wireless technology like UWB, it's very important that we put things in perspective. And anytime you see the technology evolving, and ultra wideband certainly is not the new or the latest one. It is something which is having a rebirth right now in different shapes and formats. But before that, I would like to put a perspective together, right? In our life today, we have the connectivity, which is just a way of life, right? As you see, the evolution has happened. The connectivity has grown manifold in our life, and we have these devices to which we operate our daily life, such that it has become the way of life. And definitely all of this is going to be wireless, right? And that is why the important thing, as you guys are from the academic background, right? In terms of technical, what you know is the spectrum which is available, the energy spectrum. And this energy spectrum is split into the radio part and the optical part. And we are going to focus on the left side of this particular domain, which is the radio spectrum up to 300 gigahertz. I would let Srivatsa and Pablo go through the basics of where the ultra-wideband technology falls. But this is for you to put a perspective that these are the fundamental building blocks before we talk about the new technology. Right? The radio spectrum is the essence of the wireless connectivity, right? And these are the different technologies which we are operating today. And why are we seeing the emergence of UWB in a stronger way? Maybe I will go through the video so that you guys have a view of what's going on, how the ultra-wideband is evolving before we go into the technical basics. Just give me a minute. I'll play the video, Manish.
Vijay, make sure the audio is enabled because it's not audible. I think reshare with audio enabled.
Yeah. Yep. I think that gives you a sneak peek into what ultra-wideband has emerging with the different possibilities. But instead of just wondering about the possibilities, let's go into the real world and start with Pablo of what the UWB technology is all about. Over to you, Pablo.
Okay, thank you. Thank you for the introduction. So in the video, I'm not sure if everybody could hear it, but in any case, we'll go over the details in a second. So hopefully you can see my screen right now.
Yeah.
All right, so what we're gonna do today, or anyway, maybe before starting, I will also give a bit of more of an introduction of myself, because I also come from the academic background, and then maybe because of that, I think that it may be interesting for some of the students that are here today listening. So basically, I was doing my PhD, and I was working basically on research on ultra-wideband, and I was trying to develop. So the key idea behind ultra-wideband is that not only it serves to send data or to transmit data, but it also allows you to do what we call ranging. And ranging is the idea that you can actually exchange wireless signals to measure distance. And that is a key thing or a key feature of this technology that actually is what it is really spreading the adoption of this technology for novel use cases, okay? And then in my PhD, I was actually doing research on novel ways to estimate distance with ultra-wideband and also positioning. And then because of that, then basically I got in touch with NXP, and then because NXP is one of the key companies that is actually trying to develop or build this ultra-wideband ecosystem, right, to change or to shape our future, our wireless future, let's say. And then they are trying to develop all these use cases, and then because of that, I also joined this company and I'm trying to help to make that vision come true. Okay. So what we're gonna do today is that I will first give a technology overview, so hopefully to give you a good idea or a good foundation of the technology. And then I will explain actually how the technology works and how it compares to other wireless technologies. And then I will actually pass the microphone to, or the video to Srivatsa, to my colleague, that he will actually explain like the family of chips that NXP is developing or has already on the market to actually develop or build all these use cases. And then he will talk also about the fun part, which are all the industrial ultra-wideband sectors and the use cases and the application that we are trying to build with this new technology, and that hopefully should really get you excited. And finally, also about the role that NXP and let's say also our jobs have on standardization, right? Because if we want a wireless technology to really be out there, we need to, between all the companies and academic industry, we need to all get together and somehow agree on protocols and systems so that the different devices or the different wireless products can interoperate, right? So standardization is super important, and then we're also investing a lot of time and effort on that part. So without further ado, maybe I can start on the technology itself, okay? So what is the key thing about ultra-wideband, and why do we even care about it, right? Because, you know, as they said before, it is an old technology. So actually 20 years ago, they were already investigating it, but then somehow now it's really taking off, right? Now we are putting it in our phones, in our cars, and in everything, right? So why is it actually important? So I think that to understand this, we need to understand maybe the impact that GPS had on our lives, right? So because of GPS, so somehow GPS told us or tell us where we are in the global world, right? So where we are in the map, no? And then how we can use, and then we get a position, and then we can actually use that, for instance, to navigate from one city to another, or to find the store that we want to visit, and that kind of thing, right? But the problem of GPS is that it works in a global scale or in a city scale, but then it doesn't work actually indoors, right? Because the signal, it gets super attenuated, and then we cannot really make anything out of it. And then this is where ultra-wideband actually comes from. So the idea behind ultra-wideband is that it's going to solve like a problem that we've been trying to solve for 20, 30 years, which is the indoor positioning problem, right? So how to understand or how to estimate where we are within a room, within a shopping center, within a supermarket, within an airport. So this is where ultra-wideband is going to come, and it's going to actually put a solution to this and resolve problems so far. And it's not only about getting our position, but it's also about understanding where we are compared to other devices, right? Because we can estimate the distance to these other devices, or we can estimate the angle to those devices. And then based on that, we can also enable new use cases that actually Srivatsa will talk about later. So the key idea of ultra-wideband then is that it's going to provide the where, the same way as GPS, but in indoors, right? Where we actually spend most of our time, and it's going to do it in a very accurate and robust manner. So here we are talking about centimeter level, right? So we really want to know where we are instead of the meter level or tens of meters that we get with GPS. Okay, and then actually from the video, what you could see is that if you use ultra-wideband, then some of the potential use cases will be that, for instance, you can measure your distance to your door, and then based on that, you can try to actually enable or open the door, right? So you could have like a smart access. Then you could also try to open your car, depending on where you are or how close you are to the car. Or you may even control some smart devices inside your home, okay? And these are some of the potential use cases that hopefully will get you excited about this technology. Now, to get a bit more into the details about why this technology or this wireless technology is a bit different, we need to look a bit into the spectrum, okay? And if we compare ultra-wideband with most of the other wireless technologies, normally we have a narrow bandwidth, right? So we have a bandwidth of, let's say, 1 megahertz or 20 megahertz in the case of Wi-Fi. But then in ultra-wideband, what we're going to do is that we are going to transmit very short pulses in time. So it is kind of impulse radio because you send these short pulses in time. And these short pulses, they translate to a very large bandwidth that is in the order of 500 megahertz. And then because of this bandwidth, which is a unique thing in ultra-wideband, then we're going to get some special features that we can actually have with this technology. And so actually the special feature is that we can, this large bandwidth gives us like excellent 10 resolution. So we can determine when the signal actually arrives at our device, okay? And then based on that, we can estimate distance or the time of flight, and then the distance, and then our position and so on. And then the good thing of this is also that because the way that the radio works, then we transmit pulses with very low power. So it is an energy efficient technology, especially compared to Wi-Fi, for instance. And then the other good thing is that because we spread the energy across such a large bandwidth, then we also limit the interference to other technologies, right? So that these different technologies, they can coexist, okay? And that is very important also in the spectrum. Now, how do we get such a large bandwidth? So the main idea, and more or less you can see it from this picture over here, is that we're going to transmit very short pulses in time. And here what you see is actually like a typical ultra-wideband pulse multiplied by the carrier, right? Because So not only you need to transmit the pulses, but then you need to put them in the right frequency band, right? So then here what you see is actually the pulse multiplied by the frequency, so that we get a very large bandwidth, as you can see in the bottom figure, center around the frequency center or the carrier frequency, which is where we want our frequency band to be, okay? And then, as I said before, so the cool thing or the unique thing of this technology is that the bandwidth, because of these very short pulses, is going to be very large, in the order of 500 megahertz, which compared to the typical Wi-Fi channel, which is around 20 megahertz, it is significantly greater, right? Significantly larger. And the same happens with BLE. And this is going to enable this excellent time resolution that we exploit from ultra-wideband. Now, another key thing for ultra-wideband to actually be adopted right now is the fact that it is standardized. It is standardized in the IEEE 802.15.4 standard that actually defines the PHY and the MAC, right? And then based on that, we can actually build these new chipsets that actually have this rate incorporated, and then we can enable these new use cases. Now, to give you a bit better of an overview of the standard, so normally the standards, they actually define how the frame should be and how the radio more or less should be, right? And here we actually saw like the most important parts of a frame. So normally you have a preamble, and this preamble in this wireless system is used for synchronization, because essentially you have two devices that they want to communicate to each other, and then they need to somehow synchronize, and then so they can hear the signal. And this preamble is actually very important because basically, or the way it works is that you transmit a sequence of pulses, and the pulses, they can have different polarity. Okay, so you see like this is a positive one, and then maybe the red one is a negative one. And then the idea is that you send a sequence of pulses that actually the receiver knows the sequence and the transmitter, so they agree, let's say, on this sequence. And then using a cross correlator, you can actually estimate the channel impulse response, and then based on that, you can get the time of arrival of the signal, and then the time of flight, and then the distance, and so on. Okay. So the idea is that we send this sequence of pulses, and then we're going to exploit that to actually estimate the time of arrival of the signals. Anyway, so this is the preamble, which is the very first part, and it's a very important one. Then it follows by the standard frame delimiter, which actually tells you when the frame actually starts. And then we have here like the last addition of the 802.15.4c standard amendment that was released in 2020. And this addition is the STS, which is actually like the scramble timestamp sequence here. And the idea there is to transmit a sequence of pulses, but then this sequence is defined by a crypto key. And then this crypto key needs to be, let's say, known by the devices. Otherwise, you cannot basically resolve it, and then you cannot cross-correlate. And then this thing or this feature is actually super important because it's going to give us security, right? So because of this STS that depends on a crypto key, then we can make sure that the distance that we are measuring between two devices is secure and is accurately measured. And that is very important because, for instance, if you want to open your car, then you want to be sure that you are, let's say, I don't know, 3 meters away from the car before you open it, right? Otherwise, someone might come and actually steal your car, right? But this STS enables this use case and many others, and it's a super important part. And then it follows by the physical header and then the PSDU that actually have a different modulation scheme, but we are not going to go that much into details there. So why it is important is that we send the preamble that actually synchronizes the devices and also enable us to measure the time of arrival, and then this STS that give us the security aspect that we actually need to enable real world use cases. Okay. Now this is kind of the technology overview, or very brief technology overview that I wanted to give. Let's say about ultra-wideband now. Now I want to actually go into the details about how do we exploit wireless signals to measure distance or to measure position. And here is basically where ultra-wideband is going to shine, and it's going to actually become super important, or it's going to become like the key technology to enable many use cases that Srivatsa will talk about later. So there are different ways in which you can actually use wireless signals to measure the distance between different devices or to measure the position. And the most widely used one, until now at least, it was based on the signal strength, or the received signal strength of So basically you transmit a signal, then you receive it, and then you look at the power that you get from that signal. And it turns out that basically there is an equation, that is the path loss equation, that defines that basically as the signal travels through the distance, then the power, the received power, it becomes lower and lower, right? And then based on that path loss equation, then based on the received signal that you have, then you can try to estimate the distance between two devices. And this has been widely used in the literature because it is very easy to measure. So normally every chipset actually is able to measure the received power, and based on that and based on a few other parameters, then you can actually try to estimate the distance between two devices, okay? Unfortunately, when you measure the distance based on the received power, then you suffer from a lot of variations or fluctuations, and then there is a lot of variance that you don't want to have in a very accurate system. That is because you have multipath effects, then you may have new obstacles, or then the other things can happen, like fading, signal fading, and other things. And then because of that, you have this fluctuation, and you will not have the accuracy that you need for many use cases. So normally what happens is that in a short range, it may work relatively well, but you may still make 1 to 3 meters error. But then as you go farther away, then the curve of the path loss, it actually flattens out. And then at that point, you cannot really estimate anything that accurate, okay? But anyway, but this signal strength is a very easy indicator to get. And then because of that, it has been widely used in the literature, but then it will not enable very accurate distance estimation or positions. Now, another one that is actually becoming more and more important, actually because of Bluetooth and also ultra-wideband, is to measure the angle of arrival or angle of departure. Normally, the angle of arrival is most widely used. And then the idea here is that, so you receive a signal and then you try to measure where that signal, where is the orientation of that signal, where is that signal coming from, okay? So you try to estimate the angle at which the signal arrives in your device. And how do you do that? So to do that, what you do is that normally you have a multi-antenna system, or possibly with multiple receivers as well. And then what you do is that because the signal travels a little bit more to one antenna than the other, right, depending on the angle where the signal comes from, so that small distance or extra distance translates to a phase difference of the carrier that you have. And actually that carrier, and then applying some trigonometry and so on, you can take that phase difference and you can try to estimate the angle from where the signal comes from, okay? And then if you have like a few receivers that measure this angle, then you can actually do what they call triangulation, and then you can try to estimate the device position. Now, this is a very cool feature and it's very nice, and it is under development, and then they are really trying to make it work. But then one problem is that if you really want to have very good accuracy, it is hard because you depend on multipath, especially if you use Bluetooth. And then it is also tricky because you may need to have like a multi. So normally the more antennas you have, the higher the accuracy that you can get. And then because of that, it becomes a bit costly because you need many antennas for this. And then it also becomes hard if you want to have 360 degrees of field of view, okay? Then, so in Bluetooth, they are doing this because they send this continuous wave signal and then they change the frequency and then they try to estimate this. And then another way in which they are trying to exploit these continuous wave signals in Bluetooth is to try to estimate the distance based on the phase. And again, it's a nice approach, but then, and it can achieve good accuracy, but then because it is with Bluetooth, then it is more error prone due to multipath as well, right? And finally, the one that we are actually interested in today is about the time of flight. So the time of flight, the main idea is that you want to so you want to estimate the time a signal takes to travel from one device to the other. And that is what we call the time of flight. And then knowing the speed of light in air, which we know, then you can translate that time of flight to the distance. And once you have the distance, then you can do all sorts of things, okay? And this is what we are going to focus on because it is actually one of the key features of ultra-wideband. And so I will explain in a second how it actually works. But the good thing is that in ultra-wideband, then you can measure this time of flight, the distance, but then you can also measure the angle of arrival, and then potentially you could combine these techniques, and then you could have, for instance, like positioning with a single anchor, with only one fixed device, right? Because you measure the distance, and the distance gives you a circle in which you are, and then you measure the angle, and then at that point you know where this device is located. So now allow me to get a bit more into the details of how this time of flight actually works and how it is, for instance, important, and how it also compares to other radio technologies. Okay, so this time of flight is one of the key features why ultra-wideband is now really being adopted, and one of the main applications for that, or one of the early application that was really fostering the adoption of this technology, is the smart access to your car, right? Like, for instance, you may replace the key fob, and then you may allow, for instance, to allow a user to open the car, for instance, with the phone, right? So if the phone has ultra-wideband enabled. And for instance, one way in which you can do that is that you simply try to measure the distance to the car, and then if the distance is below a threshold, maybe you try to open the car, okay? So in the simplest scheme, so the simplest ranging method in which you can estimate this distance is by doing what we call the single-sided two-way ranging scheme. So, and in this scheme, what happens is that let's say an initiator, in this case the key fob, will transmit a packet that we call the poll, and then after a given time delay, the car, in this case, will actually reply with a response. And it's also the scheme that we see over here, okay? And then in its way, the signal actually suffers from this, or the signal has to travel the distance, and then because of that, it incurs a time to travel that distance, and that is the time of flight. And what we're going to do is that we're going to measure the transmission timestamp and reception timestamp of each message. That means we want to measure, and that is what ultra-wideband enables, we want to measure exactly when we transmit the signal and exactly when we receive it. And we want to measure that with less than a nanosecond error, okay? Like super accurate. And then what we're going to do is that, let's say we measure those timestamps, and then at that point we have the time delay, which is this TCAR here, or the time that it takes for the car to reply. And then we also have the time between the transmission of the poll and the reception of this response. And actually, if you have these two times, then you can compute the time of flight based on this very simple equation over here. And once you have the time of flight, then you can, knowing the speed of light in air, then you can translate that to the distance. So maybe to give you a bit more of an intuition about how this works. So the idea is that by doing these chains or other more elaborated changes, then we can estimate very accurately the time of flight with centimeter level accuracy, right? And this is very good and it's awesome, the fact that we can, based on these two signals, actually measure the distance between two devices with such an accuracy, right? And this is actually achieved because of these very short pulses in time, because they give us this excellent time resolution to estimate when the signal arrives, okay? And then based on that, we can estimate this time of flight very accurately. Another good point of this is that even if we have some obstacles, like for instance, like the body in between the key and the car, then ultra-wideband actually serves to measure this time of flight in this sort of non-line of sight conditions. And then the other benefit is that compared to Wi-Fi or BLE that typically use, for instance, RSSI, so the received signal strength, compared to those technologies, this is super accurate, right? So we're talking about centimeters or decimeters of error compared to meters of error, okay? Now, the other good point is, or the other key point is that it is a standard. So we have a standard behind this technology that actually allows us to build upon the standard and to build the technology and so for the different companies to agree on the physical layer to use and so on. And the standard also defines like different ranging methods, like the one I showed before, but then also some more elaborate methods to even achieve higher precision or higher accuracy, okay? And finally, another key thing is this fact that, for instance, in NXP, our products, they have this dual RX design, and that actually allows us, so we have two receivers with two or more antennas, and then based on that, we can also measure the angle of arrival. And then not only we can measure the distance, we also measure the angle, and then we could potentially estimate your position. And here is an interesting picture because it is actually the key signal that we use to measure the time of flight or the time of arrival. So the way that this technology works is that you send this sequence of pulses that they are known at the transmitter and the receiver. Then you cross-correlate, and then you get an idea of the channel impulse response, which is this signal over here in one case, okay? And then what you are going to try to do, or what the radio does, is that it measures the time at which this signal arrives, and then based on that, we estimate the time of flight, okay? Now, some more details about why ultra-wideband is very good compared to other technologies. And one important aspect is, so how does it work when the signal is blocked, okay? So ideally, what you want to measure is the direct path or the direct distance that the signal travels from one device to the other. Unfortunately, in some cases, this signal may be blocked, right? And then because of that, then you may get a reflection. And then because of that reflection, then you may have an error in your estimate. And then this is what it is reflected in this figure over here. So you have the transmitter, you have the receiver, and then there is a wall, or for instance, there could be a person, or there could be like a table or whatever. And then the direct path may be blocked, okay? And then because of that, then the receiver may get a direct path that is slightly attenuated, for instance, and then it may get also the reflection. And the good thing in ultra-wideband, because the radio sends such a short ultra-wideband pulses, the good thing is that we may still receive the direct path pulse directly followed by the reflection. But because the pulses they are so short, we can still distinguish them. And that is one of the key features that is actually going to improve the accuracy of this technology, especially compared, for instance, with other narrowband technologies, like for instance, Wi-Fi or BLE, that as you can see over here, so the blue pulse is the direct one, and then the red pulse is a reflection. But because of the way that the signals are, then they are going to sum up together, and then you're going to get this green signal from which it becomes more and more difficult to estimate the actual time of arrival of the signal, okay? And then because of that, then it will be more difficult to estimate the time of flight and the distance and so on. All right. And another thing to, let's say, to understand why ultra-wideband is very good in this case is that there is actually a relation between the bandwidth that you have. And I showed at the very beginning that ultra-wideband has, or the name actually says that it has a very large bandwidth compared to these other technologies. And there is a relation between the bandwidth and your ability or the ability of the wireless radio to estimate the time of arrival, okay, or the time of the signal, okay. And then as you can see in this kind of figure here, is that with ultra-wideband, because of the large bandwidth that we have a spatial or range resolution in the order of centimeters, while for Wi-Fi, maybe in the orders of meters, okay? And then because of that, then we get very good accuracy and precision with ultra-wideband. Some more details maybe to convince you a bit more about why this technology is cool. So because of these short pulses, then the good thing is that we're going to be able to estimate very accurately the timestamp, so when the signal arrives, and that we derive from the first path, that is from this channel impulse response signal that I showed before. Then because of the large bandwidth that we have an accuracy in the order of 10 centimeters in line of sight conditions. And then also because of the very short pulses, then we can distinguish the direct path from multipath components, which is going to allow us to have such a great accuracy. And then we can also estimate. So you saw that we only need to change 2 messages to estimate the distance. So because of this and the time that these packets take to transmit, then it's going to be so we can actually estimate this in a very short manner, right? So in less than 1 millisecond, potentially, we could have the distance. And that is very good compared to, let's say, what you could do with other wireless technologies, okay? And almost to conclude from my side, this is a graphic to actually give you a better intuition about why ultra-wideband is cool and why ultra-wideband is now being really adopted. So with many other technologies or other wireless technologies, what we see is that we try to estimate the device to be located, the orange point here, and then we are measuring it. But then because, for instance, of the short bandwidth, the narrow bandwidth that we have, then we cannot estimate the distance very accurately, okay? Now with ultra-wideband, because of this large bandwidth, then this uncertainty area becomes much shorter, right? Or it gets reduced, because then we get tens of centimeters of error or precision, let's say. And then because of that, then we can estimate the distance of this device very accurately, right? And then if you even use NXP, UWB chipsets, then the cool thing is that we have also this dual receiver architecture. And then based on a single reception, then you can also estimate the angle from which the signal comes from, okay? Then for instance, if you look at that in 2D, at that point, from the distance, you get the circle where the device is located. Then based on the angle, then you know from which part the signal comes from, and then you can estimate the device position. And that you can do in a very accurate manner, in a very robust manner, and even in the case that there are some minor non-line of sight conditions, okay? So hopefully with this graphic, you get an idea about or why ultra-wideband is actually providing such good or this accuracy and why it becomes super useful for many use cases, okay? And now maybe to give you a bit of to wrap up my part and before I pass the mic to Srivatsa to give you a bit of a summary about why ultra-wideband is becoming adopted. So first of all, because it is super accurate, so it's going to allow you to estimate the distance between two devices in a very simple manner with an error typically below 10 centimeters. And then it also allows you, especially if you have this dual receiver architecture, it also allows you to determine the angle, okay? And then based on the combination, you can already estimate the position. It is a very robust technology because as we are sending these short pulses, then we are very robust against multipath components that are one of the key issues that we have with many wireless systems. And that is going to enable us to have better accuracy and precision. Then it also has a very good, decent range. This is the communication range, how far the signal can travel and how far we can actually estimate distance. And it is, let's say, in the order of 100 meters in line of sight conditions. Then it's also a secure technology that allows us to measure this distance in a secure manner. And that is because it has this STS part in the signal, which depends on a cryptographic key, okay? Then this key needs to be agreed between the two devices, and based on that, we can estimate the distance in a secure manner. And finally, it also enables, because it takes so short to estimate the distance, it also enables real-time use cases and applications where we can estimate, let's say, the position of a device in a latency below 10 milliseconds, for instance. And hopefully these specs, they actually get you excited about the technology. And now when Srivatsa talks about the use cases, then we can actually convince you a little bit more about why it is useful. So I pass over the microphone to you.
Thank you, Pablo. Excellent. I think so. I really enjoyed it. So I remember my college days and a good professor talking about the technology and teaching how it is. It was really good. So let me start going through the next part of the presentation. So why it is so important, this technology, how it has, how every other important companies in the industry are really want to go with this technology. So in NXP, what we call is dimension family. So let's look at the user perspective of things here, right? So a user who is carrying a mobile phone uses this mobile phone to unlock his car in a secure manner. And at the same time, you have a laptop where the user authenticates his ID with the laptop and it opens. He doesn't need to key in his password or anything there. And the same user wants to operate a smart home speaker to control the volume, etc. And at the same time, he wants to control the smart TV. Now, going into the same thing, look at the overall dimension in it, in the user is operating here. You have an automotive sector where he's operating his unlock and doing the process with the car in a secure manner. And you have consumer electronics, a laptop, and you have the smart speaker and the TV, which belongs to IoT sector. Not only that, and it's also about the secure opening of the door lock. he doesn't need to carry a key for a car, need to carry remote for some. All these devices need not carry a key for the home, right? So everything is there in this in his mobile phone. Now, what we talked about UWB is about bringing in such kind of secure accuracy, estimation, localization with it. Bring it all together in one device and look at the perspective of the user, what it gets over there. The potential of UWB is immense over here. So what it addresses the use case or the problem it solves, you can imagine for that matter. In the previous slide, we talked about accuracy of a particular object with plus or minus 10 centimeter. You might have faced this problem in your real world, right? Some people might be using your Bluetooth headset, and there are chances that you will keep losing this Bluetooth headset within your home. And you open up your app and try to find, it says that, yeah, it is somewhere in your home. But where? You go and ask your parents where it is, and you know what the answer you get back from them, right? So now, if you have such kind of angle of arrival and the distance accuracy with it, if the location says that, hey, the particular UWB or based earbud is next to the couch or fallen under the couch, you go and pick it up, right? So it's such kind of accuracy that you can expect when you're actually applying it to the real use cases. Now, building the ecosystem over here, what happens when you bring all these things together, right? So you might have an Android phone, you might have an iOS phone together, and you have this ecosystem there where you have automotive, where different OEMs making the car, and you have different OEMs making these IoT devices, and the industrial ecosystem things. How do you ensure that this one particular mobile phone is able to operate all these things and still interoperable, right? So this is a big challenge, and that is what something needs to be solved to make it really universally applicable device. So that is where NXP has put its effort into all these three dimensions. That is where it is called Trimension, where it is automotive, industrial and IoT, and the mobile device. So for addressing each of these needs in different ecosystem, NXP has different chips to go with. You have Trimension SR150, so Trimension SR40, and automotive enabled chips. So all these UWB chips addresses different use cases, application, and at the same time, all these are interoperable. So that is the big advantage when you have this kind of unified solution here. So if you look at the Trimension, what is that we are trying to achieve over here, right? So run UWB autonomously thanks to the embedded software. So which means that you have a mobile phone, and everybody knows that a mobile phone application processor within itself is a power hungry thing. Now, when you want to open your car door lock or want to open your house door lock, you don't want to take out your phone and look at the application and try to open it. What you do, you just keep your phone in your pocket and you walk to the car. And there the ranging happens, right? So here what happens is that the application processor itself is in sleep state. It is not woken up, but the UWB within inside this with this embedded firmware is doing all the job what is needed for the user. So you walk near the car, secure ranging happens, nobody is able to penetrate what it is, and then you securely open the door lock. Now, there is no need for real-time interaction from the host processor, right? So that is a big thing when you see an independent edge computed microprocessor, which is doing all these things for you. Now, how do you then make all these applications interoperable, right? So that is where the standardization comes. You might ask, you have IEEE and you have these standardization. What exactly is the bridging between these standardization? So that is what I would take an example. Let's say you go to a restaurant, you pick up the menu, you see 100 of items in that menu, right? But you don't need those 100 items. What you need for you at that moment, for your own need, you pick up those from the menu and you will order and you will get it. That's exactly what a standardization body does. An IEEE is an exhaustive things of specification which says how do you get this technology working. A standardization will pick up these things and ensure that these devices are interoperable in nature. So that is a big thing. So what standardization body does, that the devices which claims that I support this technology provide certification so that it ensures that the interoperability is possible among those devices. Where it happens? So currently there is FIRA, which is a standardization body where the PHY and MAC development are specified, and these developments are done within the firmware and which resides in the UWB IC. Then how do you interact UWB IC with the host processor? There is another standard over there, which is called UWB command interface, UCI, which is over SPI or I2C. Now, all these specifications are developed in accordance with FIRA Consortium. So here the FIRA Consortium is a standardization body which has immense expectation and participation from multiple OEMs in this field. Now, what does each of these processors supports in itself, right? So SR150 has the dual RX for AOA functionality. 3D AOA is possible. Not when we talk about AOA, it is not just 3D plane; it's the complete 3D AOA that we are talking over here. So you exactly know the azimuth, elevation, all those angle of arrival that can be computed over there. So you have RTOS and Linux software solution, which can cater to multiple different platforms belonging to IoT and the mobile world. And when you apply these things to very small things, right? It's like coin cell operated kind of a thing. So you might have seen today in the market about these trackers, right? You have Samsung Galaxy, Smart Tag, and other things. So all these things are operated by coin cell. Now, each of those things needs to be handled in a way that they are all power efficient and runs for a longer time. So for that kind of a family, NXP has a solution which is very power efficient and which applies these technology into perspective to solve this use case. Similarly, on the automotive side, you have the chip which resides on a key fob, which caters all these application needs, and it has SDK of its own. Similarly, a standalone MCU which can solve the use cases there. Now let's look into the details of industry UWB sectors, right? So you have healthcare, you have safety and security, agriculture, manufacturing, mining, warehouse logistics, and building control. Now, how do you use this in any of these fields? Right? So let's start picking up one thing that what UWB does today, right? So we talked about in the very beginning about the UWB technology. Now we talk about how do you use this for indoor positioning? Why it is so important, right? So when you're talking about indoor positioning, you talk about a way you use your mobile phone to do untracked navigation. What do you mean by untracked navigation over here? It's so important when it comes to privacy of things here, right? So let's say you are in a shopping mall or in a basement of a big shopping mall where you are finding your own car, but you don't know where you have parked it. Suppose if you have the UWB provided over there, you have a static map, you pick up on your phone and you navigate yourself to the location where you have parked your car. So amazing, right? So you don't have to depend on something else. And at the same time, the advantage is that nobody else is tracking you on where you're walking, right? So this is so important for somebody with privacy where they don't want to be tracked over there. UWB provides strong localization in non-line of sight scenarios. So we talked about reflection, refraction, these kind of paths. And let's say you are in a parking area where there are multiple cars over there. Right? So in such cases, UWB does provide very good localization with non-line of sight scenario also. Now, if you apply the same thing to a bigger things, right? So if you want to navigate yourself in a shopping mall, or let's say there is a big warehouse where there are multiple things kept over there, and you want to understand which of the items has certain expiry, what it belongs to, where it has to go, all those things. If you see this picture over here, what it says is that there is a factory area over here. You have a lot of inventory control that is happening. There is a process routine optimization that is happening, and there is also the drone control that is automatically tracking all these things. if you see this and you apply it to big warehouse factories, so how many people are needed actually to track individual things, individual items to say that this particular thing should have been sent much beforehand, or it's up to the time, these kind of things. You apply UWB as a localization. Suppose if these, let's say a particular item in a rack 4 has a UWB tag over here, which is transmitting its signal to the anchors which are kept on the roof of that warehouse facility. You are then able to see the movement of this particular parcel among different aisle. So a person need not manually track in which aisle this parcel has moved into. Rather, it's a system generated information which says that item A belongs to aisle 5, floor 4, right? So this is so accurate and it reduces so much of burden on maintaining these inventories over there. Let's see how it is done. So for example, you are talking about the mobile food device as a tag, and you have anchors which are mounted on the roof. All these anchors, what you see, which are mounted on the roof, are all synchronized, are all time synchronized to a switch, which is there in on the infrastructure side where the localization engine is running. Then you have each user walking around that area. Now, then what happens? These anchors in itself are doing ranging. So distance between these anchors are known. The time of flight between these messages are known. So when the mobile phone receives these signals, it's able to accurately estimate its position to those anchors. Similarly, if you want to track the mobile phone among the infrastructure over there, what happens is that the mobile phone will send a blink message, which is called as one-way ranging with its transmission timestamp. And then the anchor which is receiving this particular signal will all mark the timestamp of its received signal, and it will send it to the localization engine to actually locate that particular device. This is so powerful if you look at the way the same infrastructure, what you see, where a mobile phone is doing a localization on its own, which is untracked, and also possible where this mobile phone is being tracked by the infrastructure there. Now, if you look at some more details into the protocol aspect of it, what happens, right? So you have a mobile phone which acts as a tag, and not only mobile phone, right? So if you even say that you have a small coin cell operated tag, which is there as a badge, and people are walking around in an area, and you want to ensure that you're tracking your own employees, something like that. So these tags will be sending the blink packets periodically. And for a minimum setup, you require, for minimum localization to do the triangulation, you require minimum 4 anchors and high network capacity available because of short blink packet what we have. So however, the collisions are possible. So in a way, you can randomize these blink messages that are happening so that the collision can be avoided. And the tags here, which are they need not synchronize with the network. Right. So what happens is that the tag just transmit a blink, and this blink is received on the anchors, and the synchronization happens on the network side. So all the timestamp associated to that tag are all synchronized. Now, if you see the same thing here, so you have a particular blink which is received by anchor A. It knows that it received the blink packet at a certain time interval. Similarly, on anchor 2, it knows it timestamp when it received. Similarly, on anchor 3, it received. So all these 3 anchors are placed in fixed location on the ceiling. Now, based on the absolute time of flight measurement of the tag, at least 3 anchors, right? You should be able to localize that. Now, how happens? So you are also exchanging certain the packets over there. So which you are doing the single-sided two-way ranging over here to actually compensate for the drift. And then anchor time synchronization here is not required. Then the network capacity of number of tags is less due to higher number of messages. So the protocol design will be done in such a way is that these blink packet itself takes very less time to transmit so that you have more capacity and more tags can be accommodated in the network. This is one of such use case. Let's see the more thing, right? So you might have seen this Galaxy tag from Samsung and usage of that. So here in this case, what happens, right? So it is normal tendency that people do forget their things, they misplace something, and you need a way to accurately locate these things. So you buy a tag. Let's say you are buying this tag from a particular OEM website or through Amazon or whatever. You take this tag, and let's say everything is standardized. What you do is they take this UWB tag and you pair with your phone, which means that you are identified that this is my tag belonging to my particular device. So you pair this tag, and then you enable certain privacy with it, saying that this is my device ID and nobody else should be able to locate this particular thing. The idea here is that the device you'll be able to find that particular tracker device only if it want to be found. So that is the idea when you are going to do the pairing key over here. Now, let's say you have lost a particular thing and you want to do locate where it is. So you have PLE advertise, which is very low power in nature. It will be transmitting the service ID saying that I'm the tracker service every X seconds. So to say that to make itself discoverable. So then the user wants to find, he or she opens that particular application, checks at the credential, right? So there will be a credential exchange happening so that the authentication is done to that particular mobile device and the tag. And the mobile service app discovers this particular device, saying that, okay, this particular tag is at certain distance and at the angle over there. So if you map it to a particular room, you should be then able to locate exactly where that particular tag is present. So some more into it. So the protocol aspect of it, that you have the message exchanges that are happening. So what standardization body does is that it defines what happens in this message structure to carry the timestamp information, etc. So all these will be standard. So if the user is replaced with one OEM phone with another OEM phone, you should still be able to find your tracker. So as long as all these things are interoperable, certified. So we talked about these use cases. Let's see what is NXP's role as such in the overall standardization here. So NXP leads the way over here. So for FIRA, the FIRA consortium is dedicated to development and widespread adoption of seamless user experience, which we talked before, how a particular user will be able to talk to multiple devices. And more importantly, NXP is the founding member of FIRA. Currently, there are more than 80 plus member companies, including top universities. So we have seen that there are a lot of universities who are very interested to adopt this and make significant contribution to this technology as well. Why you see the members, your top OEMs, which are there in the world today, are part of FIRA simply because the kind of interest that it has generated, and these OEMs believe that you can solve the real world problem with it. So that is the reason why you see the member companies are growing in FIRA today. And what does FIRA standardization include? So FIRA standardization includes 15.4c compliant MAC and PHY specification development, and also the service specification development. So what does service specification here means is that you define certain protocols, certain payload data to be added. All those things get specified as part of the service specification in FIRA. Now, when it is taken to certification, the MAC, the PHY, the service specification, all these aspects are taken into consideration, and a particular device is said to be as, let's say, a FIRA compliant device, which means you buy any FIRA compliant device, your phone is a FIRA compliant phone, then you can do ranging with the device. It doesn't matter which OEM, as long as they all support the standardization certificate or got certified, it's possible to do that way. So in FIRA, you see the definitions happening around how do you do a secure ranging, truly secure ranging, and the real-time localization, the coexistence of these multiple use cases together for seamless access. And also, there are use cases that are being discussed in FIRA. These are all available public. You can look into this link, what is given over here to understand the development that are happening there. Now let's look at the other side of things, right? On the car side of things. So when initially UWB development happened, it actually happened to solve the most important use case, the car theft, right? So what happened in car theft was that the insurance companies were really worried, and they kind of said that, okay, the cars which are not really secure, we are going to jack up the insurance price for it. That was something concerning to everybody, and that is where a need for a secure way of unlocking the car happened. So this started way back with CCC, what is called Car Connectivity Consortium. It is driven by many industry leaders, including NXP and top OEMs and top OEMs on the car and the mobile side in the world. So here the mobile devices managed all aspects of entry, engine start, and the life cycle of digital keys. So imagine that you have a particular mobile phone, and you have different cars. And also, let's say you are borrowing your car from your friend, or you are renting your car from the friend. How many keys that you want to carry at this, right? So it is so painful to carry so many keys there. So if you have this digital key present on your mobile phone, which is a trusted one, which is provisioned one with that particular car, you take your phone, walk near the car, and the car identifies you, and it opens the door. It's so seamless over there, right? So what happened when this particular security thing was seen? The first release of CCC happened with NFC solution, where you go take the mobile phone, tap it onto the door handle, and the car unlocks. So thereby you have a secure entry to the car. Now, you hear what you do, you pick up your phone and tap it onto the handle. Now imagine you don't have to even do that, right? You take your phone, put it in your pocket. Right? So you go there, you just open the door and you get into it. And then you share the same digital key among your trusted members of your family or a friend, how you want to do that. All these things, ecosystem on operating the car is specified in this CCC standardization body. So typically what you see in this use case flow over here is that you have BLE wake up and initialization. This is where initially we talked about in the slide about the preamble, right? So you have many RF characteristics that needs to be exchanged, and more importantly, do the authentication part between the mobile phone and the car, saying that this is the device that you need to range with, where you derive this STS with this negotiation. So the car, when you does the authentication between the phone, whenever you decide to walk near the car, all the ranging parameters are set over there. Then you have UWB ranging starting between mobile phone and the car. So this is completely secure ranging happening. There is no man in the middle attack happening. If there is any man in the middle happening, it is very difficult to attack simply because of the nature of UWB there. You are talking about 2 nanosecond pulse. You're looking at the time of flight and you're multiplying that with the speed of light to actually measure the distance, which means any alteration in the pulse over there, you increase from 2 nanoseconds to 3 nanoseconds or 4 nanoseconds, then the distance variation is in the order of kilometers, not even centimeters or meters, right? So it is that huge. So car then easily knows that there is an attacker over here, then it doesn't open that. So that is the advantage that you get. It is so hard to actually tamper the overall ranging sequence that is happening over there. Now, when it comes to localization, you are walking to a particular car, the car knows that to which door you are whether you are near the driving door or the back door, etc. Right? So those kind of positioning is also done, and that is possible and specified in the CCC standardization. So if you see the evolution of this key itself here, right? So we are talking about a very closed ecosystem where you have a particular key fob and you have a particular car and you open over there. Now look at this possibility where you have a particular mobile phone which has all these things together, and you are able to open multiple different cars, multiple different area, right? Today you are in India, tomorrow you go to US, you rent a car and you are able to open that with your phone. So that is the convenience what we are talking about it, and that is possible with UWB today what it is there. So all these protocol uses 15.4z HRP UWB, and the specification details will enable such kind of interoperability happening there. So let me go with the conclusions. So conclusion is that UWB provides the way for many novel use cases in industry, IoT, mobile, and automotive. Then short pulses translate to a large bandwidth that provide excellent time resolution for time of flight estimation, which we initially talked in Pablo's presentation. Better ranging and positioning accuracy than wireless technology. We know now why, right? So many people may have this question on, if BLE can do it, why do you need UWB? We got the probably hope you guys got this answer why this is so important and why it is differentiated between those technologies. NXP Trimension family, unique set of ICs to enable such novel UWB use cases and widespread adoption of UWB technology. Standardization efforts, right? So you need a standard. You need a standard to make truly interoperable and exploit all the true nature of solving these use cases. NXP leads the way in FIRA consortium here. Now, I hope you people are really enjoyed this and excited to join NXP and also build the UWB ecosystem. What then you need to do, right? So you can make your own UWB invention. You can come up with your own use case. It is possible. How it is possible? You can find these links in NXP UWB where it talks about our development kits which are present. You can take these development kits and you'll be able to develop your own application. What is also interesting to know is that you have the Apple U1, which is interoperable with these development kits. So you can explore the possibilities of developing use cases, taking in advantage of such interoperable SDKs. The FIRA consortium, you have the link to the FIRA consortium. You can go take a look in over there and see all the use cases, what is happening, and who are all the members there. Okay, to wrap it up, that's it from my side. Manish, want to take over here? I guess we are okay with time.
Yes, Sri, thanks. Very exciting journey. Lot of futuristic applications. I'm also, really excited with how the digital key is going to drive my car in future. Plus, yes, when we are going in the shopping malls and all, how my mobile will identify the right things and how, that's a very real use case, big parkings, at least in India, where sometime we are struggling where we parked.
Absolutely.
And with this new technology, we can identify the where we parked, or the mobile is going to, sell us where the car is parked. I think, yes, very, you can say, real-time solutions for real problems, which we are facing, in our day-to-day life. So hopefully the future is very bright, not just, by the help of this technology, but yes, our innovative, attendees will also be benefited, and they can, think of to start some innovative startups by generating real life solutions. And yes, based on behalf of NXP, we can, extend our full support in this journey. Yeah, great. Thanks, Sri, and thanks, Pablo, for all the presentation, and thanks, Vijay. Now we can start a Q&A. If any queries, guys, you can unmute yourself and you can ask your queries. Yeah, Sumit, you can unmute yourself and ask the query.
Yeah, so I think Pablo mentioned in one of the slides that this is a 2D localization because we can just find one distance and one angle only. We can't predict a 3D dimension in a space.
So actually, so the example is for 2D, but then you can estimate, of course, 3D, right? So as Subhasa was saying, for instance, if you have more than 2 antennas, then you could potentially do 3D AUA. So that means that you know exactly from from in space, let's say where the signal comes from, that you can do with 3D AOA. For example, if you combine that 3D AOA with the distance, you could already do 3D positioning, right? Then besides that, then for instance, so as Sebastian was saying, so for instance, there is the TDOA, where for instance, a mobile device sends one signal, and then the anchor infrastructure receives that message, and then it estimates the position. So based on that anchor infrastructure, then you can also estimate your 3D position, and then you can also do it by measuring two-way ranging. So with two-way ranging, you measure the distance. Then if you combine 3 distances, then you can get the 2D position. If you have 4 anchors, let's say 4 devices whose positions are known, then you actually get 4 distances. Then you get 4 spheres. Let's say in the intersection of those spheres, then you actually have the device position in 3D.
Right.
So hopefully I answer your question. So it works in 2D and also in 3D, and there are methods to do both.
Correct, Pablo. So I think we need more than two anchors in this, correct?
So let's say if you do 3D AUA and the distance, then you have the distance and you have also the angle. So potentially you could already do positioning. If you use the two-way ranging, then you need.
We need this for how many anchors we need this?
So let's say if you do 3D AUA and distance, then with one anchor you could potentially do it. If you use only distances, so that means you are doing two-way ranging, then with 3 devices you get 2D. With 4 anchors, you get 3D, okay?
Understood.
And then with TDOA, then you need 1 anchor extra. Did I answer you?
Yes, Pablo, understood.
Thank you. Any other query? Yeah, Shanu, go ahead. Unmute yourself and then ask the query.
Hi everyone. So my question has 2 parts. First part is regarding the cost considerations with respect to the current technologies. So is it cost competitive with respect to the current technologies, what we have at present for this wireless technology, say Wi-Fi or Bluetooth? And second part to it is how soon I should expect to see this becoming available like Bluetooth and Wi-Fi in my mobiles or any other device which I use.
Right. Thanks for asking that question. Probably I'll take your second question. How soon you already have UWB technology deployed? So Samsung GN20 was the first Android phone to be launched in market that has an NXP solution. So your latest Xiaomi Mix 4 that was released, that also has an NXP solution on the phone. Now, this is what is there available in the market. And also I was talking about the tracker, the Galaxy Smart Tag tracker. So these have NXP solution there. Now, coming to the other question there. So on cost effectiveness and other things, right? So each of those technologies are targeted for different use case. So with respect to solution, what you are going to achieve, what you are going to solve with it, the technology with respect to UWB and the silicons that are available in NXP are cost effective over there. So which solves the problem and also cost effective. I wouldn't try to compare, or I will never compare one technology over the other technology to solve a particular problem and trying to make it look like the other, right? We should not also do it. But with respect to UWB, what we are targeting to solve these problems are cost effective very much from NXP Dimension family.
Okay, thanks a lot.
Okay. Yeah, just a few more addition on top of that. Shanu, now I think in iPhones, few of the latest version of iPhones are having UWB. I don't know whether it's an NXP solution or some other solutions, but
It's
yes,
not,
we are.
it's not NXP. It's not. So it's on Apple's own solution.
Oh, okay, it's Apple's own solution. But that, yeah, but on the receiver side, they can interact with our solutions, right?
Yes, interoperability is possible. So yeah, even Apple is also a member of FIRA and CCC, so they are also very much committed to making things interoperable. Yeah,
so in near future, it is going to a big, innovation maybe in next 1 or 2 years. NXP is investing a lot, and I think we are leaders in this market, right? Sri and Pablo?
Yes.
Great.
Yes.
Thank you. We have next Sujit. You unmute yourself and ask your query, please.
Yeah, hi Pablo, hi Srivatsa. So my question is it possible to create LiDAR kind of depth maps with UWB technology?
Well, LiDAR what? Sorry?
LiDAR kind of depth mapping. So in augmented reality applications, is it possible with the UWB?
So, I mean, you could still do augmented reality applications because, let's say, you could know where the device is, and then you could also know where the signal is coming from. So then you could position that in some augmented reality scenario. It works different to LiDAR, but then, for instance, another use case, for instance, of ultra wideband. Actually, this was the initial use case from 20 years ago or more. It's also ultra wideband radars. So you could also potentially enable those things. But I mean, LiDAR is a different technology. So it's different.
Okay, understood. Okay. Yeah, thank you.
Yeah, basically the application is very different if you compare LiDAR and UWB. Yeah, next query is.
Sorry, maybe if I can add something. So normally, for instance, in all these use cases that we explained before, so normally you always have communication between two devices, right? So in LiDAR, you're not doing that.
One way.
So normally we have a chain of messages between two devices, and then based on that, you estimate distance, angle, and whatever. And then that's what we try to use. Then, so if you do some sort of radar, then you could actually have something more similar to LiDAR, but still different technology, different possibility.
Yeah, understood, Pablo. So could we come closer to that? I mean, to use to create a 3D model of an interior space using UWB, not as accurate as LiDAR, but could our technology come any closer to that? Because LiDAR requires specialized equipment, right? So this is far cheaper.
Yeah, so I know it's hard to say. I mean, we're working on cool things, but so this type of high precision maps that you can get potentially with LiDAR is very difficult, because here basically you are sending an RF signal, and then you depend on the reflection, and then you will need to have a whole bunch of antennas to really determine very well maybe where the angle is coming from, and then the things get complicated, right? And I think that it is also important, maybe the question before, that at the end of the day, we want to have a cost-effective solution that somehow fits into a smartphone and so on, right? And then in a smartphone, you're already very limited in space, and then it becomes tricky to enable all of that, right?
Thanks, Pablo. Thanks, Manish.
Yeah, next is Rishabh. You can unmute yourself and ask your query.
Hello, hello Shivatsa. So I have two questions. First one is, what is the maximum data payload that you can transfer with the ultra wideband in a single packet? And the second one is related to security. You mentioned that the data is transferred securely over ultra wideband packets using STS, right? Scrambled timestamp. So how is this scrambling happening? Does the NXP Trimension also has a security engine built into it?
Yes.
And okay, sorry, the third question will be with respect to digital car key. But so what protocols are there and the standardization on the digital car key, and how is NXP going about that?
Okay, I'll try to remember what the questions you asked. Probably I'll go with the first one what you have asked. The first question is what is the overall payload size, right? So the PSDU, what you talk about in UWB, the BPRF, there are two methods. So one is BPRF and HPRF. BPRF PSDU is 127 bytes. HPRF you can go up to 4K. So that is that is a payload size. So you have both these methodologies that you can do, and also to add, you can also achieve different data rates over there. So BPRF PSDU you can go up to 6.8 Mbps data rate, and you can go up to 32.1 in HPRF. So all these are possible. Now, it's also the PSDU, what you are constructing depends also use case requirement. So that is where what I was talking before on the service specification, which actually determines what kind of payload that is going to carry. That will be all part of the PSDU there. And the second part about the security, what you asked, right? It's a very important question, right? So we talk about STS, but how do you generate STS? So it's a complete system solution when you talk about it, because when you do the authentication between the two devices, a trusted device, to maintain the confidentiality between that, you will generate key pair. It could be Diffie-Hellman there. So you generate key pair, and then this key will be used to generate the STS. So if you look at a actual packet, you have a PHR, SFD, STS, and the PSDU there. So you need a way to generate this STS. What is the STS generated is 5 specified in FIRA. That is the amendment 2020 that we are talking about. The same key used on the other end would generate the same STS sequence. Now you transmit this STS sequence. At the file level on the other end, it is going to recognize this STS, what is programmed with the seed there. On the PSDU, you have done the STS. You can use the same key or the derivative of that key to encrypt the PSDU part. And on the other end, you receive this encrypted data and you will decrypt with that key, right? So that is good. So your third question, Rishabh.
With respect to digital car key, so what all protocols? So one thing I've understood. So with this ultra wideband chip, you also need some sort of a secure element or a cryptographic accelerator, which can do the cryptography job to make sure that the data is securely transmitted over ultra wideband.
Yes.
Okay. Now you mentioned about digital car key. So what are the cryptographic protocols, if you know, that are used for such transmission by CCC?
Right. I mean, I probably wouldn't go too much into detail, mainly because of the time and the details that we need to get involved. So what are the type? Basically, you have symmetric and asymmetric, both are used. So all the global platform specified thing. The secure channel derivation with SCP-03, SCP-11, all these things are possible that can be done. So it's up to the OEM and in this case NXP to decide on the use case what is the best security that can be provided, that is achievable at the system integration level.
Okay, and one last question will be, so NXP try mention if it has to be interfaced with the other NXP devices or other microcontrollers, so is it can it be integrated via standard interfaces like I2C, SPI, etc., or it requires dedicated board development?
When you say other interfaces, right? I mean, we are more importantly here, physical interface. It's a transportation logical interface that we need to emphasize here. So if you have a common agreed standardized logical interface, the underlying physical interface shouldn't matter, right? So I just take example of NFC also, what is there today, right? So you have Android open APIs present for NFC, and the way transport these configuration from host processor to the chip is through the NCA commands, which are pretty much standardized. So which underlying physical layer that you are going to transport, it's up to the integration choice there.
Okay. Thanks, Shiva sir. Thanks a lot.
Thank you. Okay.
Manish, I believe that you were mute.
I think so. Manish is done with this question now. Manish.
Sorry, Pradnya, can you unmute yourself and ask the query?
I have one question. What I understand is still PIRA is kind of a consortium and its spec is evolving, right? And you just not told there are some products which are already in the market. So as I know, AirTags and might be in some high-end Apple phones also would have it. You mentioned one Samsung GN20. So my question is, does it comply to FIRA And is it interoperable is one question, or they just operate within their family, like it's always apple to apple, or how is it?
Well, so I would say like this, right? So UWB is a very recent technology with respect to what we are trying to do in the localization, but very fast growing technology, right? So there are certain commitments what the OEMs has towards their customers, right? So when they bring in the new technology, they have their own methods to deploy it at the customer with the over-the-air updates of software and other things. So where you are today, so you are going to have much more addition of features into the spec that is happening, and it is up to the OEMs how they take this and provide their customers with the necessary feature what they think is required for their platform which can support. So so from the standardization aspect, it's an independent body which will keep on developing the use cases where these leading OEMs are part of that standardization body. They pretty much know what is happening over there. They are part of the development and committed to make it interoperable, work with all the UWB technologies there. Now, at the same time, deploying of this technology is purely a choice of that OEM, how they want to strategize with their customer commitment, etc. Which NXP for its customer will always be committed to provide the right solution.
Okay, so you mean that it depends on the OEM, how they want it, and where to stop and whether to accommodate everyone. It's the totally choice of OEM.
NXP is committed to moving forward with respect to taking the advancement which is